I'm Tobias Schaedler. I work at HRL Laboratories. For those who don't know HRL, we are the former Hughes Research Labs. We're now co-owned by Boeing and GM, but more than 75% of the research we do is for the government. We're located in Malibu, California. Have a couple more different sites also south of LA. So I'd like to talk about a new technology that we developed for additive manufacturing of packaging. There are two main benefits of additive manufacturing: prototyping capability and design flexibility. The chart on the left compares different packaging technologies. Via pitch on the y-axis is a good metric for the size scale. And on the other axis, you have cost at low volumes. So we think that 3D microprinting could fill a white space here, competing with PCB technologies as well as low temperature and high temperature co-fired ceramics, especially for applications where you don't have high volumes. So you can save on tooling costs and so on. We're not trying to compete with lithography, CMOS. If you really want to go to small micron size features, that's the way to go. And but for low volumes, the cost is high because you need to have masks and a whole clean room and everything, right? The advantages of additive with respect to design flexibility are pretty well known, but I would argue that they are even more pronounced in semiconductor packaging, where you are limited to rectangular designs with vertical vias and horizontal traces. So your design's really locked into these design guides from the packaging manufacturers. 3D printing enables more design freedom, for example, curved or angled vias, cooling channels. You can embed passives like resistors. So our objective is to develop the technology to 3D print packaging to enable advanced designs and faster design iterations at a lower cost. Now let's talk about the additive technology. There are many different 3D printing methods out there, right? In microelectronics and packaging, you need at least a dielectric and a conductor. However, multi-material printing is still in its infancy. So for this study, we focused on printing the dielectric and then adding the metal later. Our preferred printing method for dielectrics, both polymer and ceramic dielectrics, is digital light processing by UV curing. In conventional DLP printing, a UV projector exposes pixels on the order of 40 micrometers, which allows you to print parts in a couple hours, so you have a pretty good print rate. But the smallest holes you can print are typically around 5 times the voxel size. So to print vias of interest for the packaging application we're after, we have to go to a smaller voxel size. There are now microprinters available that use optics to focus the exposure down, and they can achieve 2 by 2 micrometer pixels. This allows us to print 10 micrometer features in line with our needs for packaging. However, the print throughput scales approximately with the voxel size cubed. So if you decrease your voxel size by a factor of 10, you decrease your print rate by a factor of 1,000. With a 2 micrometer pixel size, you can still print centimeter scale parts within a couple of days. And I'll show you some examples. But if you go down to smaller voxel sizes, for example, submicron with 2-photon lithography, then your print rate becomes so slow that you would need a couple of months to print a centimeter scale part. So that's not really feasible for our applications, but you could go smaller with these technologies. On the right here, I'm showing a pre-ceramic resin that we developed. So we're making siloxane resins UV curable by adding UV functional groups so that we can use the commercially available DLP systems to print ceramic resins. We've published this several